this is a tough idea to understand. The idea is that because, well, anyway, your hands are enantiomers with each other. Molecules that are enantiomers with each other have identical chemical and physical properties. But in the same way that your hands can tell the difference between each other, chiral molecules can too. So if you'll endure a little bit of an exercise, you don't have to participate if you don't want to, but go ahead and turn to someone next to you and give them a handshake with the right hand. You're going to feel a right hand to a right hand handshake. Okay? Okay, very business-like. Okay? Yes. Now, one of you take your right hand and then shake the other person's left hand and see how that goes. I mean, it starts to feel a little different, doesn't it? Your right hand can tell the difference between somebody else's right hand and their left hand. The right hand handshake is like, I'm glad to be here and I hope you give me a job. The right hand, left hand handshake is like, am I supposed to like hold it like, am I supposed to kiss your hand? So the two experiences, the right hand handshake and the right hand, left hand handshake are diastereomer experiences. Okay? Could you shake left hands? Would a left be just about the same as a right handshake? It doesn't feel exactly the same to you because our brains know the difference between right hand and left hand. But the point is that if you think of your right hand as being one chiral molecule and your left hand being its enantiomer, your right hand can tell the difference between two other chiral molecules. Okay? And biology is chiral. Biology is made of molecules that have stereocenters. And therefore, two molecules that are enantiomers with each other will interact with biology differently. Think of biology as being your right hand, and think of the two enantiomers as being somebody else's right and left hand respectively, and your right hand can tell the difference between those two situations, right? In the same way, biology can tell the difference between two enantiomers. This ends up being really important in medicine. There's a lot of detail we're glossing over here, but you need to understand just for right now that biology is full of stereocenters and is chiral. You already know this because, as I told you last time, when you look at the mirror and you see your enantiomer, you're not the same thing as your enantiomer. And the reason that you're not is because you are made of chiral molecules. You are chiral. Okay? So I want to show you an image. This is an image from what's called an X-ray crystal structure. What I'm going to show you is a structure of a protein, active site, that is bound to, well, it's an overlay of two different structures. So superimposed on the same image, you're seeing an image of a protein bound to the R enantiomer of a particular drug molecule. And then overlapped with that is another image of the same protein bound to the S enantiomer of this molecule. Now in this image, carbons in general are going to be gray, oxygens are going to be red, nitrogens are going to be blue. Water molecules are going to show up as little red dots. And this is just a type of photograph you can get. It's a technique called X-ray crystallography, but it shows you where the atoms are in a protein that's binding a molecule. So these two molecules are shown over, their structures are shown here to the right. The orange one has an S stereocenter, and the purple one has an R stereocenter. What these molecules do and what the protein is isn't important for our discussion today, but these are data from an experiment that show you that the two molecules bind differently to this protein. And if you imagine that the carboxylate group here is a thumb, and this is the palm of the hand, and these are fingers of the hand, then the orange one is your left hand and the purple one's your right hand. And you can see that the fingers of this molecule bind in the same spot, but then the thumbs end up on different sides. Okay? These two molecules bind differently to the protein. For example, in the orange one, the carboxylate thumb is able to engage in ion pairs and hydrogen bonding, which is what's represented by these dotted lines. In contrast, the purple thumb can't. It's not even in the right spot. This can have consequences. You would expect these two molecules, the orange and the purple enantiomers, to bind to this protein with different affinities. One will bind tighter than the other. And they could have different downstream biological effects. One might be a better drug than the other because it binds tighter. Okay? So the key concept here is two enantiomers will bind their particular target in biology with different strength, and they will therefore have different effects. Okay? Questions about that observation or where it comes from? All right. A couple other things you need to know to understand the story we want to tell is, and you'll just have to accept it as fact, in chemistry, it is often difficult to separate two enantiomers because they have the same chemical and physical properties. So if you have a mixture of two enantiomers, it's not like you can raise the temperature and one will boil off or faster than the other. They have the same chemical and physical properties, so they're difficult to separate. It can be done, but it's tricky and it's expensive. And I won't tell you any details about how you do it. There's a number of different methods. But just accept the fact that when you go to synthesize a drug, if it has a stereocenter in it, and if the drug is chiral, it is always easier to synthesize the drug at the same time as you synthesize the enantiomer. And it's always easiest to prepare a one-to-one mixture of enantiomers. Difficult to get one pure enantiomer. Okay, got that? So a one-to-one mixture of enantiomers is called a racemate. That's a word, or a racemic mixture. A one-to-one mixture of enantiomers is called a racemate. So this is shown here as a molecule called citalopram, and it's a selective serotonin reuptake inhibitor. We'll talk about those later on in the semester. I take an SSRI, some of you may as well, for managing symptoms of depression and so on. I'll tell you about some fun side effects later, but in general, they can do a good job of smoothing out the rough edges when it comes to experiencing depression. So citalopram was invented in the 90s, and when they invented it, as I said, it was easiest to manufacture it as a racemate, or a one-to-one mixture of enantiomers. Now, based on what I said, do you expect the R and the S enantiomer to have the same biological effects? No, because biology is chiral. Now, you hope, and in order to get the drug approved to be sold as a racemate, you have to demonstrate that the racemate is safe. There are some drugs where the wrong enantiomer, it's reasonable to expect one enantiomer to be better than the other for reasons we've talked about. It's also possible that the wrong enantiomer may have different side effects from the right enantiomer. As long as those side effects are tolerable, people don't care too much, but there have been cases such as the well-publicized thalidomide medication, which we'll talk about in the 60s, where the wrong enantiomer is actually toxic or has negative effects. And so researchers have to be careful with that. I'll say more about that in a little bit, but in the citalopram story, one enantiomer did bind more effectively, was more effective than the other, but the wrong enantiomer didn't have any horrible side effects. So if you know anything about drug development, it's really, really expensive. And in the United States, at least, a drug company has a certain number of years after they file their patent before the drug goes off patent. And what going off patent means while your patent is live, you have an exclusive license to manufacture and sell the drug and market the drug. Once the drug goes off patent, other people can now manufacture and sell the drug. This is when drugs become generic. So currently citalopram is available generic. Drug costs normally decrease dramatically when a drug goes generic because there's more competition. Have you heard of this before? Yeah. So citalopram's patent expired in 2003. And by 2009, and this is in the UK, so you have to do some, it depends on how strong the dollar is at any given time, but in the UK, 28 tablets of citalopram at 20 milligram dose was 1.26 pounds. Pretty cheap, okay? The drug company that filed the patent is often devastated by the drug going off patent because they're now going to lose a bunch of revenue. So a strategy was developed called patent evergreening. And this is a trick that drug companies use to convert an expiring patent into something that they can continue to market exclusively. And the trick is, and it works because of clever marketing, the trick is you can get a patent for a process that produces just the pure enantiomer. So the company that made this knew that the S enantiomer of citalopram was the effective enantiomer. So they developed an enantioselective synthesis, meaning they learned to make just the right enantiomer. It was more expensive to do that, but they were then able to get a patent for just the S enantiomer instead of the racemate. And that gave them more exclusive rights to manufacture and market the drug, provided they could convince physicians that it was better to prescribe the pure enantiomer instead of the racemate. Okay, so the physicians had already been prescribing the racemate for years. Then the drug company says, hey, you know that generic citalopram that's suddenly cheaper? You shouldn't give that to your patients because it contains 50% of the wrong enantiomer. You should give them this, which is 100% the correct enantiomer. And you can see the dramatic effect in about the same time frame. So the FDA approved S-citalopram, and in the trade name of the molecule that's the pure enantiomer, you'll often see ES for S, that means S configuration, or AR for R, that means R configuration. S-citalopram, they were approved by the FDA just before their patent expired on the racemate. And they got an additional 10 years. Their S-citalopram patent expiration happened in 2012. They got an additional 10 years of exclusivity here, and they would now they sold during the same time frame where the racemate cost £1.25. They were able to sell the same amount, half the dose, for 14.9 pounds. You know, almost more than 10 times as expensive. What do you think about that? Ethical? Unethical? What are the issues? Yeah, go ahead.
I feel like that gets into marketing at that point. But it's like, if the enantiomer doesn't cause too many bad side effects, then it just depends on what you want. Like if the first one causes side effects and makes you really sleepy or something, and you have a lifestyle where you need to be really astute and, you know.
So you need to do some reading, right? I mean, it was clear that the wrong enantiomer wasn't poison. If it was, it never would have been approved in the first place. And so you would have to do some careful reading to determine, as a physician or a nurse practitioner, you'd have to do some careful reading to determine exactly what the differences are, show me the data, and is it worth it for my patient? And I suppose you're right. If side effects are different for the S enantiomer than for the racemate, then maybe you could make a case to the tune of 10 times the price, right? What about the dosage there? Why do you think you only need 10 milligrams? And this is something you could imagine a sales rep who doesn't know anything about chemistry telling you, just looking at the numbers, oh yeah, 10 milligrams of S-citalopram is just as good as 20 milligrams of citalopram. I'm telling you that's the most boring thing you've ever told me, but you might be impressed why. Why am I telling you that is the most boring thing I've ever heard? Right, because 20 mgs of citalopram only has 10 mgs of the right compound in it, right? So you got to pay attention when people are telling you these things about various drugs. Okay, there's some other drug stories we could tell you about this. In terms of ethical or not, I think it's kind of a challenge. Like if I were a physician, I'm not, so I don't know. You'd have to look at the side effects. But probably it's fine to keep prescribing generic, right? On the other hand, if there are severe benefits, I just want you to be a little bit skeptical of the pure enantiomeric drugs to make sure you're not playing into some drug company's strategy for evergreening their patent. That being said, I'm also not on the side that drug companies are our enemies. Drug development is really, really, really expensive. Most drug development processes fail, so if we want medications that are going to be effective, the ones that succeed are going to have to be somewhat expensive to help pay for all the ones that fail. And so it's certainly not a solved problem, it's a challenging thing, but these are sort of the issues that we deal with. Okay, so let me give you some examples of situations where one enantiomer is better than the other, but the racemate is still okay, and some other examples where, say, one enantiomer is better than the other and the one that's wrong is kind of a major problem. So, for example, let's see. Levofloxacin is an antimicrobial molecule. Here's its structure. Got a fluorine here, a nitrogen, another 6-membered ring. I know as I'm drawing this, somebody's going to ask, do you want us to memorize that for the exam? And the answer is no. I'll be clear when I want you to memorize molecular structures. For now, I just thought maybe you'd be interested to see what drug molecules look like. So this is levofloxacin. The stereocenter is here, and its configuration is S. It's antimicrobial, but the R enantiomer is possibly neurotoxic. So that's a good case for, hey, let's make the right enantiomer and only make that one. And that's the current one. The S enantiomer is the one that's currently manufactured and marketed. Another example of good enantiomer, bad enantiomer is ketamine. You guys heard of ketamine before? Okay, what is ketamine used for? Okay, pain, analgesic, I think is, but yeah, a painkiller. What others? So I'll draw its structure, and I'll draw the S enantiomer, and this is marketed and sold as S-ketamine. Do I have the structure? Oh shoot! Oh, there it is. All right. So it's a 6-membered ring. You got a ketone here, a nitrogen, an amino group, a methyl amino group there. Me stands for CH3. I do that sometimes when I'm in a hurry. I'll just write the CH3 there. Then there is a benzene ring attached to that same carbon that's got the nitrogen and a chloro group. There is one stereocenter, it's there, and the stereocenter is S. For ketamine, the S enantiomer has painkiller and anesthetic effects. The R enantiomer can be hallucinogenic and can cause agitation and restlessness. So that's a case where you wouldn't necessarily want to use the other enantiomer as a painkiller or an anesthetic. There are interesting possible uses for both of them in treatment-resistant depression, though the S and the R enantiomer have different effects. Thalidomide is another. This was prescribed. It's still used, but is still used for various things, but certainly not used for pregnant women anymore. Thalidomide was prescribed in the 60s as an antiemetic. That means prevent you from vomiting, and in particular for morning sickness. And the correct enantiomer was fine. The enantiomer that has this effect is the R enantiomer with an H group here. So this is the stereocenter and its configuration is R. The R enantiomer was, as I said, an antiemetic, and so this was good for morning sickness, but the S enantiomer was a teratogen. Anybody know what that word means? Go ahead. Uh-huh. Yeah, cause developmental problems with a gestating fetus. And that's exactly when you're morning sick in pregnancy, and that's exactly when you don't want teratogens to be exposed to. So, and it turns out you might say, well, let's just make the pure enantiomer, and then we could only prescribe that. And this is true for some drugs. Sometimes through various chemical processes that we'll talk about, the drug can what's called racemize, meaning the right enantiomer can get converted back into the wrong enantiomer anyway. And we haven't learned the chemistry that would explain that at this point, but for example, we can understand it briefly. Imagine this proton here, which is at the stereocenter, were somewhat acidic. Imagine a base removed that proton. Let's draw the conjugate base of thalidomide, where a base removes the proton from the stereocenter. What is the hybridization of this carbon? You want to say sp3, don't you? Is that the right answer? No, it's not, because I'm asking you about it. But if I weren't asking you about it, how could you tell that this carbon is no longer sp3 hybridized? What's it adjacent to? Yeah, and when that happens, you can do this kind of thing to generate an alternative resonance structure that looks like this. Notice that that carbon is sp2 hybridized here, so it must be sp2 hybridized there. sp2 carbons are trigonal planar. Is that thing a stereocenter anymore? No. Meaning this conjugate base is not chiral. And when it reprotonates, when it picks up a proton back from the base and goes back to thalidomide, it's got to do so equally from both sides. So you're going to get both the R and the S enantiomer. So there's some medications where even if you administer just the one enantiomer, they're going to change stereochemistry. Racemize, or another word for this is epimerize. They're going to change configuration of the one stereocenter. So that means this drug is not safe to be given to pregnant women in any dose well, not safe to be given in any stereochemical form. It's not safe to give just the R enantiomer because the biological processes will make the S enantiomer. Okay, another one that maybe is a little bit more boring than these sort of horror stories of teratogenic or hallucinogenic or neurotoxic effects. Ibuprofen. So this is one that you can buy. It's sold over the counter. It's sold as a racemate. Here's the structure of ibuprofen. Do you want to know where the IBU in ibuprofen comes from? This set of 1, 2, 3, 4 carbons with that arrangement is called an isobutyl group. IBU. Hey, Grandma, you want to know where the IBU in ibuprofen comes from? It's a carboxylic acid, and it's got a stereo center there. The S enantiomer for ibuprofen is 160 times more active as a painkiller than the R enantiomer, but biologically, the R enantiomer gets converted through a process similar to the one I showed you in thalidomide, gets converted into the S enantiomer. So it's pointless to make just the pure S enantiomer, because if you give, it's sold and administered as the racemate, if you give the racemate to a patient, the 1-to-1 mixture of R and S, the portion that's the S enantiomer is going to do its job. The portion that's the R enantiomer is either going to be less effective or get converted to the S enantiomer. Either way, you're fine. Okay? So it's kind of complicated, right? Oh, a pure an enantiomerically pure drug is not necessarily better. In the case of ibuprofen, it would not be worth the cost to make just the S enantiomer. In fact, it would be a waste of time and money. So anyway, these are things that you want to be aware of and think about. There's more stories we could tell, and there's whole papers. If you want to read a paper on PubMed about this kind of thing more, I can send you a link. But our last couple of lectures in this class, maybe our last 2 or 3 class periods, are going to be going through the major classes of drug molecules and talking about their mechanism of action, how they do what they do, what they're used for, and I think that'll be interesting. Okay, this concludes the material for midterm exam 1. So you're now prepared. Good luck. May the force be with you. But we're still having class tomorrow and Wednesday, so hang in there. It's going to be a wild ride.